In this video, they want us to use the node voltage method to find the voltage VO, which is the voltage across this 6K resistor right here, right? So the first thing we're going to do is we're going to identify all of these central nodes. I know this is an essential node. I'm going to call this node 1. This is an essential node right here. I'm going to call this node 2. We have another essential node right here. I'm going to call this node 3. And finally, we have an essential node at the bottom here. And I'm just going to call this node 4. But instead of writing node 4, I'm actually going to take this as our reference node. So I'm going to take this to be our reference node. Now I'm going to begin to write node voltage equations at each node. Starting at node 1, I'm going to write node voltage at node 1. We're going to have a 12 volt source in this branch by itself. Therefore, this is going to make our work a whole lot easier. So we know the voltage at node 1 is just going to equal to the value of that voltage source. Therefore, we can say V1 equals 12 volts. So this is going to be our answer for the voltage at node 1. Now this isn't our answer because they want us to find the voltage VO, which is the voltage across a 6K resistor. But knowing the voltage at node 1 might be able to help us in the long run. Okay, let's continue. So we're going to now write a node voltage at node 2, right? Now when we start to write the node voltage equation at node 2, we're going to have the difference between these two voltages divided by 6,000. So we have V2 minus V1 divided by 6,000 plus we're going to have V2 over 3,000 because we're assuming the current is flowing this way. So we're not going to write it in terms of I, but we're actually going to write it in terms of Ohm's law. So we always want to write it in terms of the voltage over resistance if we do not know the current. So we're going to write V2 over 3,000 plus we're assuming that the current is now going to flow in this direction, right? Because we always assume the current is flowing away from the node. Now when we look at this, we have a voltage source that is going to be between two essential nodes. Now let's see if we know the value of the voltage at one of these nodes. For node 2, we don't know the value of the voltage at node 2. And when we look at node 3 now, we do not know the value of the voltage at node 3. Therefore, we have a special case where we can use the supernode method. Okay, so we're going to now ignore this voltage source for a second, and we're going to continue to write node voltage equations for node 3, which is going to be the second node that this voltage source is connected to. So we're going to take the voltage difference between V3 and V1. That's going to be V3 minus V1, and the resistance is 12,000 plus we're going to have a current flowing in this direction as well, and that's going to be V3 over 6,000. I'm not going to use this voltage VO because it's just going to introduce another variable, right? I'm just going to stick to the variables I'm already using. So I'm just going to say V3 over 6,000. Do not let these problems scare you, right? We're using the node voltage method. Just be aware on how you're going to write those equations. And all of this is going to equal 0. And remember, we're no longer finding the node voltage at node 2, but we're finding the node voltage at node 2 and node 3. So I'm just going to say node voltage at supernode. Okay, now that we have this, let's just simplify this. So when we look at our denominators, we know the LCD is going to be 12,000. We're going to multiply each term by 12,000. That's going to give us 2V2 minus 2V1 plus 4V2 plus V3 minus V1 plus 2V3, and all of that equals 0. When we simplify this, that's going to give us negative 3V1 plus 6V2 plus 3V3, and that equals 0. Okay, now we know the value of V1 is 12 volts, so we can just plug in V1 into this equation. That's going to give us negative 3 multiplied by 12, which is V1, plus 6V2 plus 3V3 equals 0. Therefore, we're going to be left with 6V2 plus 3v3 equals 36. And I'm going to call this equation 1. So this is equation 1. 6v2 plus 3v3 equals 36. Now that we have equation 1, we know we had to do the supernode method, which means we now have to write the constraint equation for the two essential nodes that had the voltage source between them. So that's going to be V2 and V3. Now when we look at this 6-volt voltage source, we can see that the positive terminal is going to be connected to node 2. Therefore, we're going to say that node 2 has a higher potential than node 3. So when we write our constraint equation, we're going to write it as V2, which is the voltage at node 2, minus V3, which is the voltage at node 3, equals 6 volts. V2 minus V3 equals 6. Okay, now that we have this, I'm going to call this equation 2. So now when we look at this, we have two equations and we have the same exact unknowns. Therefore, we can just solve for these unknowns by using either the simultaneous methods or we can just do the matrix method. I'm just going to do the matrix method. So we're going to have a 2 by 2 matrix and a 2 by 1 matrix, right? So for the 2 by 2 matrix, we know the first equation is going to have a positive 6 and positive 3. The two unknowns is V2 and V3. And for the first equation, that equals 36. Now for equation 2, we're going to have a positive 1 and a negative 1. And that's going to equal 6. So we're going to take the inverse of A, multiply it by B. And when we do that, that's going to give us V2 equals 6 volts and V3 equals 0 volts. So we've successfully found the voltages at all of our nodes. We know the voltage at node 1. We know the voltage at node 2 is 6 volts and the voltage at node 3 is going to be 0 volts. Now, when we look at this, they want us to find the voltage VO, and we know the voltage VO is going to be the same voltage that's going to be at node 3. Therefore, we know V3 equals the voltage VO. Therefore, we know VO equals 0 volts because the voltage VO is going to be the same voltage at node 3 and we found that to be 0 volts. So this is going to be our answer for this particular problem. VO equals 0 volts.